Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am very happy to have Marbely Micolta with us today. Hello, Marbely.
Hi,
How are you?
I'm good, and it's cold here, so
Cold.
it's
Oh,
chilly.
no. Where's cold? Where's here? Where's cold?
I'm in Michigan, Ann Arbor, so
Oh,
yeah,
that
we're
is.
not getting the worst side of the snowstorm, but we're getting
Mm-hmm.
the cold.
I bet. So it is January 10th of 2025 as we record this, and I'm in Phoenix, and we are chilly, but we're not probably as cold as you are. Is there snow on the ground? Do you get snow?
It's supposed to snow today, but there is
Okay.
no snow yet.
All right. Get there and make some snow angels or something. I don't know. That's great. Very cool. Oh, and I should ask, Marbley, what's your position there?
I'm a grad student, a four-year grad student at the astronomy department here in the University of Michigan.
Uh-huh. And when do you finish? When do you anticipate graduating?
So I anticipate 5 years, so a year and a half more or less.
Okay. All right. Well, we're getting close. We're getting close. So I'll be the maybe the first to say, well, congratulations, Dr. McCulta. Very
Thank
nice.
you.
Very nice. And as part of your trajectory there, what is it you like to do for research, Marbley?
So I like the study of Tauri stars, young low mass stars,
Yep.
where they have the protoplanetary disk, and I'm interested into like the early stage of planet formation. So when you still have the disk and you have like try to understand what the dust is doing, I really like thinking about the rocky material,
Yep.
which is not necessarily everybody's like the gas and
The
the
big
carbon.
giants, the big giants,
And
the
like,
big
what
ones.
about the rocks? The
But
rocks are
we
interesting
want Earth
too.
2.0. We got to make Earth
Yes.
2.0, right? It's
Yeah.
like, yeah. Very cool. Very cool. And that is going to bring us to this very awesome APJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Using the calcium-2 lines in Tauri stars to infer the abundance of refractory elements in the innermost disk region. And Marbly, take us away.
So to begin with, I will acknowledge my co-authors, especially Nuria Calvet, who is my advisor here at Michigan.
Uh-huh.
But everybody had a big contribution, even if it's just the modeling or just the observations part.
Cool.
Uh, yeah, and we can start with a little bit of background.
Sure.
I mentioned protoplanetary disks, and we know they're surrounding these young stars that are accreting material from the disk.
Mhm.
So normally you look at the ALMA images and you see this big, beautiful uh, disk.
Yeah.
And I'm looking essentially at inside one AU, so the
Okay.
very inner parts
Okay.
the dust is sublimate and returns to the gas of the disk and is getting into the star into the accretion flows,
Yeah.
what we call the accretion flows.
Cool.
Um, and it provides a very interesting part of like what is the remaining rocky material that reached that inner part of the disk.
Okay.
Like what's the abundance of these the rocks that we're getting there? Because we're seeing a lot of planets with the exoplanet surveys that we have that are like a 1 AU or even inside that.
Right.
So we want to like see like how did they form there even to begin with? Or like did they migrate there? Or like where is that dust that form
Yes.
those rocky materials?
Okay.
So I do that using the calcium lines as a proof from refractory material.
Okay.
Refractory material is, just to be clear, it's the material that takes very high temperatures to sublimate and turn to the gas. So we're talking about like 1500 Kelvin.
Yeah. Okay.
That's why we like calcium to prove this like material that will always be in pebbles. So we won't lose it
Hmm.
through gas processes.
Right. Right.
So
Right. Right.
we're probing all the DOS mechanisms.
Okay. I'm with
Um,
you.
yeah. And we have known to be depleted in some other stars, especially Herbig stars. So
HH.
we're trying to extend that to like low mass stars that we kind of wanted to expand it to lower mass where we see a lot of planets,
Okay.
terrestrial planets. And I'm using, again, the calcium lines to produce these materials. So they form in the accretion flows. that I mentioned. So this flow of material from going from the disk towards the star.
Okay.
So by that, we're probing the abundance of the inner gas disk. So what it really is left to.
Yes. Okay.
So
Very
yes,
cool.
I'm using, for observations, I'm using 70 stars. So of 3 star-forming regions. So I'm doing Lupus, Chameleon 1, and Orion 1b.
Okay, here we go.
So yeah, we had 70 stars in total. They have both, they're not the youngest, they're about 3 to 5, but also goes
Yeah.
not the oldest, but reaching the oldest stages of the Tauri star. So when you start having disk dissipation and you no longer have that many disks, that's the Orion 1 region.
Yes.
So and also allows to probe like if there is an age transition with this abundance that we see.
Right, because we got
All this data is public. It's the Chameleon 1 data is from Manara, and the Lupus 1 data is from Alcalá, and the Orion 1b data is from this actually wonderful program called Penelope. It's PI from Manara, and it's just taking stars from different regions of different ages to try to have a survey with age.
you.
It's also public.
Very
Yeah. I use, like I said, T Tauri stars that can be separated into two. So classical T Tauri stars are these stars that I mentioned
yes.
that are accretive material. So I also have data from what we call weak T Tauri stars
Okay.
that are stars that have the same ages, but they evolve faster and they're no longer accreting.
Okay. Okay.
So that's a good, we use it as a probe to measure the activity of these stars because these young stars are more active magnetically than main sequence stars.
Yes.
We also want to have that probe of like what's the base level that these stars will have and what's the excess that
Okay.
we see because of accretion. That's the classical T-Tauri stars.
Cool.
That data is also public from Manara too.
Cool.
Yes, so that's the observation part. That's all the data that I have that bring us to the model that I'm
Quite a
using.
lot.
Yes,
Like,
all the data parameters are independent. So all the parameters that I use.
which is a fairly massive table. I encourage people
Yes, they're
to
huge.
check it out. Check it
Yes.
out. It's good. It's very good.
Yeah.
Okay, so we got the strong
It has,
peaks and we get into the model here. Okay.
yeah. Like I say, these stars form like accrete via these accretion flows. And the way the model is called, it's magnetospheric accretion model, which is a big name. But essentially what it consists is that the magnetic field of the star truncates the disk, and then the material follows the magnetic lines onto the star, from the disk into the star.
Okay.
So
Okay.
that's where the magnetospheric accretion model comes from.
Okay.
I'm using CB Multi, which is a program made by Muserol, based also in his work and Harman 94 work. It assumes a dipole geometry, and you characterize the flow by the how far away it goes, the internal radius, and how wide it is.
Yes. Okay. Oh, here it is. Okay. Yes.
Yeah. And then you have the accretion rate of the star.
I'm not.
Is the amount of material that it's actively falling into the star.
Okay.
And that will give you the density of these flows.
Okay.
We also have a semi-empirical temperature law
Okay.
and the inclination of the line of saw. And what we added to this is the abundance of calcium. Like
Cool.
what is the extra parameter to it.
Yeah.
And we do it in reference to the solar abundance, which is what is expected to these stars to have, according to evolutionary models. So all stars are expected to have solar abundance of material. And if we detect any variation of that, like particularly depletion of that, we're considering like, well, material is getting trapped, right?
Okay.
The question is how. But if there is no if the abundance of hydrogen is solar, and
Okay.
then you don't have the rocky material falling into the star,
Yes.
then there is something else that causes the rocky material not to be in the flows.
Yes.
This brings us to the interesting point that this material is all in rocks, in pebbles, and it should be returning the dust sublimation radius when you reach those high temperatures to the gas.
Yes.
If it's not in the gas, then it's trapped outside.
Correct. Yes.
So that's our goal. That's what we want to check.
Right. Because
And
reservoir.
so we build this enormous grid of models. It's over 700,000 profiles.
Wow.
Yes.
Wow. Okay.
Spanning several spectral types and again, several the space parameters that we have for our observation. So the accretion rates goes from
Wow.
-7 to -10 solar masses per year. I say this in log space.
Yes.
Uh,
Yep.
and this is just to like surround the observation space. And the way I compare these, so this is the methods, the way I compare the models to observation is that I use the line luminosities.
Yes. Okay.
Yes, so I calculate the line luminosities for the profiles that the models generate and the observations, both the classical Tauri stars and the weak Tauri stars.
Right here. Cool.
So, and that brings us to actually figure one.
Okay, let's slide down to figure one. Some of the
Yeah.
okay, relatively cool results. And let's go to figure one comparison of calcium 2. Let's blow this
So
up.
this is
Okay.
it's a busy plot, so I will go careful with it. So in the y-axis, I have the line luminosities that I get from the light fluxes,
Okay.
from the calcium K line and the hydrogen line.
Mm-hmm.
In the x-axis, I have the accretion rate,
Okay.
and the color gives the abundance of the models. So the idea is that if a star doesn't have the same amount of material falling into the star for calcium, the hydrogen is always going to be there, right? Because it's hydrogen.
Hydrogen.
Yes,
It's everywhere.
that's why we use it as a baseline.
Yes.
So that's why we use H alpha as our control line.
Mm-hmm.
It will tell us what's the behavior of the gas.
Yes.
It's also very traceable to the accretion rate to get the density of material falling in.
Good. Okay.
And then based on that, you can also have what's the amount of like luminosity of calcium K line that you will get. But if this star has less material falling in, then the luminosity of the line of calcium decreases.
Yes.
So that's why we use the ratio, because
Okay.
as the ratio for a given accretion rate, you will expect a certain amount of line luminosity.
Oh, true.
If you
Okay.
have less line luminosity, then the ratio decreases and it no longer matches what you would expect it to have.
Good. I'm with you. Good. Okay.
And then the accretion rate, we have it for observations were measured independently from the UV axis of the.
Okay.
So that's the accretion rate in the table, the bigger table of the parameters.
Yeah, because it's falling down the
So
line.
to not have an overlap. And then we can see the models are showing color again with the abundance being solar. It's the 0, the purple. And then the lower you go to the red, the more depleted the model is.
Yes. Okay. I'm with you.
And the important part here about the Whittier stars that I mentioned is that they also form like this base level of what you can observe
Okay.
with the activity. So that's the actually like you can see the washout colors in the back. You have like
Yeah.
a very bright models and then you have like a gray out models.
Yes. Okay.
So
Yes.
the gray out models are the models as they are, and then the brighter color, the saturated colors are the models with the Whittier star. So this is the model plus what you should have as a base level just because of activity.
Got it.
And I plot my observations on top of them. So what is really cool from this plot is that you can see right away that
Got it.
for a lot of stars, there is no particular, that there is no way the models can reproduce the line fluxes
Okay.
if
That's a
it's not
bummer.
depleted. Because in like these regions of colors, for example, the purple, which is the
Uh-huh.
solar abundance, and here I'm plotting all the line ratios of all the parameters of all the lines of all the like geometries and accretion rates and temperatures combinations that you can have
Yes.
if it's solar abundance.
Mm-hmm. Mm-hmm.
So there is no combination of parameters that make sense physically with
Okay.
respect to the observations that will give you that ratio unless the abundance is lower than solar.
Yes, has to be depleted out. Yep.
Yes, it's
Uh-huh.
depleted out.
Uh-huh.
So, and we see it in a lot of stars, so that also was exciting for us because it seems really common. And if you go here too,
Yeah. Okay. Okay. And then, okay, let's do a histogram of those. Okay, here
yeah,
we go.
this is the abundance, but now it's plot without log scale. So one is solar, and then it reaches to 0.01.
Okay. Okay.
And you can see how the majority of the stars are actually depleted, which was, I think, one of the most like interesting results. So, like we see
Yes.
depletion, it's very common.
Yes.
Most of the stars seem to be depleted. Lupus and calcium have a very similar behavior, which have similar ages.
Yeah. Mm-hmm.
And then Orion 1b, which is our older region,
Yes.
seems to be all the stars are depleted,
Uh-huh.
which
Yes.
was another interesting point. Because we will assume, well, maybe this is an evolution point. However, there is a caveat that this sample is smaller than the lupus and chameleon one.
Okay.
That's future work also to do.
We'll come back to that. Okay.
Yeah, we'll come back to that.
We'll come back to that.
So
Okay.
it's a very nice hint to like there may
Yeah.
be some
Yeah.
evolution into the abundance that we see.
Yeah. Nice.
Yes, so as this came out, we were like, okay, but we want to know if it's related to some property in the disk, right? Because it must, again, if we don't see the calcium, it must be trapped outside the sublimation point. There is something in the disk that is happening.
Yes. Yes.
So we try to find correlations with stellar parameters.
Okay.
If you go to figure 3, it's right there. We try to find any correlation
Okay.
with mass, and
Okay.
we find there is none. There is no correlation. They're everywhere. Uh,
Everywhere. Yes.
yes. Um,
Okay.
which is an interesting point, but like one of the things that you just have to try out to see. We have the same story with the radius of the disk.
Okay.
There is no correlation with that. I think that's
Figure 4, maybe.
figure 4, maybe.
That's an M dot.
That's an M dot. Well, that was my next point.
Okay. So,
Yes.
so let me just recap that.
Yes.
There's no trend with calcium abundance nor with necessarily with the radius
Yes.
of where the disk ends.
Yes.
Okay.
There is no correlation with the
Okay.
size of the dust disk.
How about M dot?
Yeah, how about M dot? This is where we start to fry our brains because we find a correlation, and it
Okay.
was counterintuitive to what we thought we would get if there was any, because you see we have less calcium, so it's more depleted,
Yes.
it's less abundant with the higher accretion rates.
Yes.
We initially thought that if we have a high accretion rate, we have a lot of material falling in,
You would pick up more of the
then
calcium.
it will pick up, right?
Yeah.
Because it's there.
Hmm.
And we get exactly the opposite, which to be truthful, we don't fully understand what's going on with this.
We have a mystery.
We have a mystery. Yeah, I will come up later with that.
Oh, good. Oh, I hope you're going to solve the mystery. Okay.
Yes. And then we started to try to see correlations with the presence of substructures in the disk.
Okay.
So we know like with ALMA that these have rings and gaps and substructure. So we were like, okay, that's a sign of dust trapping, right?
Yeah.
You have a pressure bond, you have dust trapping, whatever the mechanism is to form the dust trap. Because it can be planets, it can be magnetic MRI, it can be some sort of instability.
Yes.
But what you cannot deny is that if you have some kind of substructure pressure bump, you will have dust trapping.
Uh-huh. Yes.
That is there.
Agreed.
And if it's you trap the dust, then it won't reach the inner parts, so will deplete the inner regions. So that's where we were going with this.
I'm with you.
Yes, so that will be, I want to say figure 5 or
Yeah, let's slide on down. Relation with MDOT, relation with disk structure. That's what we're talking about.
yeah.
And figure 5 is probability density.
Yes, figure 5.
Okay.
So yeah,
Okay.
yeah. So here I'm showing this is all the stars, and they're colored by whether they're a full disk, a transitional disk, or they have substructures. So we classify substructures as they have some accumulation, but there is not an open, like
Oh, rings or
a
something.
ring, or
Yeah,
there
yeah.
is like
Okay.
you can see there is like over densities, but there is no clear thing about it. And
Okay.
it's very interesting because the first thing when we noticed that is that all the transitional disks were depleted, which was a great like relief in our theory. We was like,
Okay.
okay, this makes sense because
Okay.
you have a pressure bump, they're depleted.
Okay. Is that the point of the vertical dash line here?
Yes, yes, this is marking the abundance value for what we see
When
zero
it's
point 0.7.
truncated.
So this is the below that is all the transitional disk.
I'm with you. Yep.
We have the substructure disks are all over the place, so they can be very depleted.
Mm,
And they also can be, they're never like really solar, but they can be higher than the
like
transitional disk.
7. Yeah.
Yeah.
Mm-hmm.
But that also depends of like, again, it was our exploratory kind of project.
Okay.
So we have to be like, okay, maybe there is an overdensity, but there is no significant trapping in the inner part of the disk because ultimately we're seeing the innermost, like inside 1 AU, the dust sublimation
Uh,
point, it's like 10 AU less. So maybe what's in the outer parts of the disk is not affecting the inner parts of the disk, which is another point.
okay.
And then we have a lot of full disks that they're also all over the place. We have the majority being depleted.
Yeah.
But brings another caveat, is that not all the stars have been observed with high resolution ALMA.
Okay.
So we cannot rule out the presence of substructures in there.
Fair enough. Fair enough.
Some of these stars, like we even could have some very inner, smaller substructures that cannot be seen. So we cannot rule out that for these stars. So we can say full disk all over the place, but we cannot rule out there is substructures there.
In them. Yes. Until we
Yeah.
get Alma. Alma. And we'll come back to that too. Alma. Okay.
Um. Again, in our search of properties with this, we also try to do with the dust mass, which is figure 6. Again,
Mhm.
we see nothing.
Oh,
So that brings us to like our question, like, well, maybe the dust of the disk, the mass dust of the disk,
okay.
the radius of the disk are very outer region properties.
Yeah.
So, and we're seeing something that's very, very in the inner part. So that brings us to the discussion that, well, maybe these are probably tracking different things. That
There you
these
go. There
dust
you go.
properties.
Ah, okay.
Uh,
R68. That was
yeah, that's the radius one. Yeah,
radius one. Yes. Correct.
nothing.
Yep. Nothing. It's
Yeah.
all over the place. Okay. Chromospheric limits. Bias was a bias. Line luminosities and figure 8. Want to go there?
Yeah, yeah.
Okay.
Yeah. So we were just this discussion that we're tracking different things. So
Yeah.
the house like properties that we get with ALMA are tracking the outer disk,
Okay.
and then we're seeing the innermost part of the disk, so it might be some finer structure or something that we don't see.
Okay.
And that can also bring us to the accretion rate problem that we have, like a backwards expected.
Yes.
Because the accretion rate is something that it's happening 0.1 AU inwards.
Yeah.
And then this is very outer property. So it's the depletion might be happening larger scale all over the disk or inside, depending on the case.
Okay.
But the accretion rate is tracking something that it's only very inner disk.
Yes. Okay.
And then we have this discussion
Okay.
because if we plot the accretion rates of the transitional disk and the full disk, we have a very similar distribution of them.
Mm-hmm.
So even if you have a gap, the accretion rate is not seems to be affected, or like there's no significant difference in the trend
Right.
between the two of them. So
More.
that brings another point to like, oh, you have the accretion rate is very inner, and then whatever happens in the side of the disk, it's a separate thing.
Okay. Mm-hmm.
Um,
Okay.
yeah, it was an exploratory project.
Yes.
I think like in summary, we find the biggest thing is that we find depletion everywhere. We find depletion and
Yeah.
we find depletion everywhere.
Everywhere. Yep.
So it's there. It's something that to consider. Like more than half of the stars are depleted. But 57% of the stars have abundance lower than minus 0.30 of
Okay.
solar.
Mm-hmm.
I skipped this mention, but I did when we have the uh, linear regression, I did the statistical test to determine if there is a trend or if there is a significant correlation.
Right.
It's all in the paper.
Right.
The only significant trend or correlation that we found was the accretion rate that we discussed, but I did the statistical test for every single property that we tried to find something. We
Okay.
also did a correlation test between the distributions of the abundance of the for the different star forming regions. So there might be a trend with the age that we saw with Orion, but the sample is too small, so we cannot really confirm.
Right. There were hints. There were hints, but
Yes, there were hints. That's the best we can say.
yeah.
Transitional disk. So we have big gaps. They're all depleted. Also a very important result. And yes, we find no correlation with the outer disk properties.
Right.
That seems to indicate that we're studying different things. Like this is
You're looking at different things
very inner disk versus whatever is happening in there.
there. Mm-hmm.
And our results also as part of the discussion. It's they agree with first of all, they agree with the fact that just depletion given just pressure bonds or even radial drift. Radial drift will give you depletion too.
Mm-hmm.
However, that for these ages, the depletion should be already solar, so that's why we assume that we should have solar. We shouldn't have an enhancement given radial drift.
Certainly. That I agree with.
Yes.
I'd be stunned.
So if we found depletions lower than that, then there is maybe some cases of where radial diff is more effective. We don't know, something to explore, or it's just the pressure bumps. That's another point for all those full days that we find depletion and we don't really know if they have substructures or not.
Okay. Yeah, because it's not resolved. Yes.
And this is basically the paper.
Very cool. Very cool. Okay. Very nice. Beautiful work. Beautiful work, Marbely.
Thank you.
And thank you so much for walking us through your very awesome article. That was great. So you touched on it a couple of times as we went through. So let me go ahead and push on that a little bit. Where do you think we go from here, given the published article? You mentioned several times this is exploratory. So what sort of extra things would we want to do in order to resolve some of the mysteries here on these systems? Are there more observations to do? Are there additional models to consider? Is there laboratory astrophysics maybe on some of the lines, things along these lines? So where do you think we go from here, given the published?
Yeah, so I'm actually working more observations and more modeling. So we're now observed Taurus, which is also a region that's younger.
Uh-huh.
So there might be some interesting parts here. And I'm also observing more stars of the Orion old regions to
Okay.
have more sample, bigger sample of the
Yes.
older than 5 million years.
Okay.
So those observations are underway. Um, I've been working with Taurus, some observations I have with Taurus now to do a more detailed modeling because
Okay.
it was very like we have a big sample. So we do the flux ratio,
Yes.
but that gives us an estimate of the abundance, but that doesn't give us like a proper defined, like very detailed modeling of a particular object. So
Uh-huh.
doing that now,
Okay.
very like cases that we find very interesting to try to pick up those.
Cool.
And also, like there is a lot of things I'm thinking to do. There is the SED modeling of this star
Yes, yes,
in
yes, yes.
infrared.
All the wavelengths, get them all in there.
Yes. So there is work I'm doing with Spitzer, proposing to JWST to try to see
Nice.
also the archive of JWST that it comes out to try to see what we can see in the mid-infrared, that it will be more outer disk
Yes.
and to draw comparisons.
Yes. Good.
Um, Also extending the work from calcium to magnesium, which is another refractory material
Ooh,
that's
good.
more
Good.
known
Yes.
there.
Yes.
And then we can compare what the emission lines tell us of magnesium to the opacities of the silicates in the mid-infrared with the SED,
Yep.
which it's a promising thing is if we get the two things together for a few targets, then we can do like maybe some very nice work
Right.
of finding the two things.
Cool. Very
Yeah.
cool. Well, that'll be really awesome to see over the next couple of years, particularly as your thesis comes together. It'll be really great.
Yes.
Very nice. And that'll do, everyone. And I hope this made your Tauri Astronomy Day just a little bit better. And we will see you on the next one. Bye bye.
Thank you.